So this is lecture 3, and we're going to start to talk about some properties of statistics. And in particular, we're going to talk about an important property of statistics called sufficiency. So let's really jump right into it. So as we said last time, what we're going to be working with is our setup is going to be that we have a random sample, and it's going to be a random sample from some distribution, f, parameterized by some parameter theta. And theta is going to live in some space of possible parameters. We can call it capital theta. Our definition of sufficiency is going to be that a statistic t, or to be more formal, it's a function t of our x's, is sufficient for our unknown parameter theta if the following is true. The conditional distribution of our data, f of x, given t, the statistic is equal to some value little t. So this is a function of our values little x. If this conditional distribution is free of theta. Okay, so let's box this in and let's talk about what this definition is. So we have a statistic t, and we have a parameter theta. We want our statistic t to capture all of the information about theta. And sufficiency is basically the mathematical way of codifying that t captures all the information about theta in the sample x tilde. So some statistics might be better at capturing this information than others. We're going to talk about kind of exactly what that means and practically what that means. But sufficiency is going to is the adjective we give to a statistic if we take a sample. The sample is going to tell us something about the unknown parameter. If it tells us, kind of captures all the possible information about that unknown parameter that can possibly be squeezed out of the sample, we're going to call that statistic sufficient. Sufficient for theta. It sufficiently captures all of the information about theta. The mathematical definition is that the conditional distribution, if we condition on the statistic, there is no more information in that conditional distribution about theta. So what this is saying is that conditional on knowing that my statistic is some particular value, so that t, and here I'm being lazy, I'm not saying t of x, but t is a random variable. It's a function of my random variable x, and t depends on x, and so it's a random variable. If I know that this random variable takes on a particular value, so I know something about it, conditional on the fact that I know t takes on 5 or 7, the remaining, that is the kind of leftover, the conditional distribution of the data doesn't have anything else related to theta in it. So when I say free of theta, I mean that the distribution formula, if you will, doesn't depend on theta. Theta does not appear in the formula. Let me write that more legibly. So theta doesn't appear in the formula. So the joint distribution of the data will involve theta, right? It involves theta in some way. But if I tell you what t is, there's nothing left in that distribution about theta. That is, all of the information about theta has been kind of excised out of the data, and you're left with something that tells you nothing about theta. Conditional, if I know t, there's nothing left in my data. That's what this statement is saying. The formal definition is that a statistic t is sufficient for the parameter theta if this conditional distribution is free of theta, right? And this is my notation for conditional distribution. X here is my vector, is my collection, my sample, bar conditional, t is equal to t, and then of course it depends on, you plug in my conditional distribution the particular values of x. So this, again, little x is just a vector of numbers. Capital X here is this random variable. And t here is just a number. Okay. So let's look at an example. Before we talk about the example, I want to talk about a little trick for calculating probabilities. And this is going to seem totally unrelated to sufficient statistics. It's not, and we're going to use it, and it's going to make explaining this a lot simpler. So let's first of all just get this out of the way. So forget about sufficient statistics for a moment. Let's talk about probabilities. If I have a statement, if I want to make a statement, probability that x is equal to little x. So here, again, x, capital X is my random variable. Little x is just some number. And I also want to say that x is in some set A. So here, A is just some arbitrary subset of Rn. Doesn't really matter. It can be anything. So this is a kind of weird statement to make, because it's saying, what's the probability x is equal to some specific value in Rn, and x is in some set in Rn. You can think of this as like making some statement about x. So let's draw a little picture here. Rn. And I'm going to draw my set A. There are two options here. Maybe I should draw two Venn diagrams. Two options. Number one. Here's my set A, and here's my little point, little x in A. In this case, my probability statement that x is equal to little x and x is in A is kind of redundant, because as it turns out, little x is an element of A, and so basically the first event is a subset of the second event, and so you can basically ignore the second thing. This is just the same thing as saying the probability that x is equal to little x, because that's the more specific event, right? It's basically a subset relationship. But the probability that x is in A is equal to little x and x is in A. well, it's just the probability that x is equal to little x. That's option 1. Option 2, here's Rn again. Here's A. I could choose x outside of A. Seems like a really dumb thing to do, but we could do it. In this situation, again, my probability calculation is 0. Because the intersection, let me just write this out, the intersection is empty, right? And, of course, is basically an intersection. So we could write this more simply and say that if I want to make this kind of weird statement that x is some particular value and that, so my comma is and, that x is in some set A, you could write this as the probability that x is equal to little x times the indicator that little x is an A. So why am I allowed to swap capital X here for little x here? Well, if x is equal to little x, surely we can do that swap. And this is exactly what we wrote above. In one case, it's just the probability x is equal to x if little x is an A. So if little x is an A, if little x is not an A. In the other case, if little x is not an A, this whole thing is 0. So it's exactly there. It's a case statement, right? Okay. Let's take this one more logical step. So this seems weird. Let's bring it back to statistics. So we could write, let's say we could simply summarize as this. What we might be writing, what we will be writing, is the probability x is equal to little x and maybe t of x is equal to some value little t. Say. But this is just one particular choice of A. There's some A where this is true. And so similarly, so this is just some particular choice of A, we could just summarize this as x is equal to little x, indicator that t little x is equal to little t. Same exact deal. One could summarize it in this way. Basically, there's two choices. Either the little x we choose, when plugged into our function, gives us little t, in which case it's just the probability that x is little x, or it doesn't, in which case there's no possible way for that to happen. You can't have x equal to little x and x be not equal to little t. Okay, so let's go back to, so keep this in mind, that we can kind of summarize these things in a simple way. There's a shortcut here. So this is our definition of sufficiency. Let's look at an example of sufficiency. So here's our example. Let's assume we have x1, x2, and x3, and they're going to be IID from some Bernoulli distribution with an unknown parameter theta. And we want to estimate theta. We're going to use a statistic to do that and let t be the sum of these three. Now, the sum of Bernoulli should be binomial, so this should be a binomial 3 theta. So here theta is our probability. You could use p instead, it doesn't really matter. And so here's our sample, here's our proposed statistic. Is t sufficient for theta? That's a question. Is there a better statistic that captures all of the information in theta or not? Well, we can use our definition, right? What's our definition? Our definition is that we need to look at the conditional distribution. I'm not going to write it like this, of x given t is little t. Maybe a nicer way to write this out. The conditional distribution is, of course, the joint distribution of x and t. Let's write it this way. So we know from 451 that I can write this as the joint distribution of x and t at little x, little t, over the marginal distribution of t. All right, this is just a 451 fact that f of x given y is little y is f of xy over f of y, right? Our notation is a little more cumbersome with t's, with these x tilde, but that's all it is. So let's start filling in the gaps here. As it turns out, right, everything here is discrete. So the PMF here is just a probability function. So we could just rewrite this as probability that x is little x and t is little t over the probability t is little t. This is why we brought up this. Because I can simplify this by saying this is just the probability x is little x as long as t is little t. Or, yeah, let's leave it like that. That's good enough. Over the probability that t is little t. So, what was our definition of sufficiency? Let's go back and look. It should be that this conditional distribution does not depend on theta. If we can show that it's, quote, free of theta, then our statistic is sufficient. So we've gotten this far. We have the data. We have the statistic. What we want to do is show that this statistic is sufficient by showing that this thing doesn't depend on theta. What's the distribution of the data, right? Our marginal distribution, marginally these are Bernoulli. And so let's just as an aside here, right? F of little x, right, is everything's discrete, is this thing, right? This is the product of the marginals where n goes 1 to 3. And it is, what's the Bernoulli distribution? It's theta to the xn, 1 minus theta to the 1 minus xn. Yeah, and we'll leave it like that. So that's cool. And then we do need a distribution of t, right? And that would be, t, of course, is what? It's a binomial 3 theta. So we have that f of t, which is such a probability t is equal to little t, is what? 3, choose t, theta to the t, 1 minus theta minus theta to the n 3 minus t, right? That's a binomial distribution. And so we can start filling in here. It's, I guess we can simplify this one a little bit, right? It's theta to the sum of the xn's, 1 minus theta to, you're going to get 3 minus the sum of the xn's. You push that multiplication through. You're just combining the exponents, right? Just add together the exponents. So what we get is theta to the sum of the xn's, 1 minus theta to 3 minus the sum of the xn's. That's on top. We have this indicator function. We're really not going to worry too much about it. And we get, in the bottom, 3 choose t, theta to the t, 1 minus theta to 3 minus t. Notice, of course, that as long as t here, which is my sum of the x of n's, as long as this is true, right, little t is going to be the sum of my x of n's. And so this is t, this is t. As long as my indicator function tells me that's true, that's what's going on. And so we're going to get a bunch of cancellations here, right? Theta to the t cancels with theta to the t. I mean, t is just the sum, right? That was our statistic to start off with. So that sum of these. 1 minus theta, you know, this is going to cancel with this. And we're basically going to be left with 1 over 3 choose t. You can, you know, say indicator that, you know, the sum of the x of n's is equal to t. You don't really have to worry too much about that. But the punchline here, no theta. So it's free of theta. So what's happening is that I have my data, I propose a statistic, I can show that this marginal distribution is free of theta. And so t is sufficient for theta. So that shows sufficiency. I did it kind of slowly as a first example, but that shows sufficiency. We notice that, you know, I made this whole rigmarole about this indicator function and this whole thing about these probabilities. It didn't really come into play that much, and so frankly, people tend to just leave them off. I'm being a little bit, because it's our first example, I'm being a little bit tedious here. But in future examples, we don't really need to worry about it too much. Okay, let's look at another example here. So, example, let's just take a random sample from some distribution. We don't even need to know what it is. And we're going to let t be the order statistics. The minimum, second smallest, third smallest, all the way up to the maximum. So these are called the order statistics. And we can recall, for the order statistics, that the joint distribution of the order statistics, right? If we just looked at the joint distribution of if we just look at joint distribution of the data, it would be it would just be this, right? Product n goes 1 to n. And if we want to look at the joint distribution of the order statistics, so here we have a bunch of order statistics, right? So t is a kind of n-dimensional statistic. Not a very good statistic. It doesn't summarize a lot. All it does is order them. But it's allowed. And so t in this case is t is also going to be basically an Rn. The theorem, which you may or may not recall, is that the joint distribution of the order statistics is basically the joint distribution of the data we place an n factorial out front. So here, again, here little t has basically n components. Looks a bit scary, but it's actually not so bad. The question is t sufficient for theta? Are the collection of all of the order statistics jointly sufficient for my unknown parameter? Notice we haven't done anything about this distribution. It could be any distribution. So in order to check this, what we would do is you would say, what do I need to check? I need to check that if I look at the conditional distribution of x given t, we need to show that this doesn't depend on theta, right? So again, we can look at the joint distribution of x and t at little x, little t, over the marginal distribution of, well, marginal, but the distribution of t. And again, so last time we made this big deal about this indicator function. Basically, you only need to consider, the whole thing there is that you only need to consider where t of little x is little t, because otherwise it's 0. It's just not going to matter. And so let's write out what the joint is. We can basically play that same trick, and we can basically say this is f of x at little x, right? Why was I able to get rid of the t there? We're playing the exact same trick as here, right? Same thing, absolutely same thing. And say this over ft of t, and that is, well, what's the joint distribution of the data? It is this, and in the basement we have an n factorial, and then we have a product. Okay. Now it doesn't look like it then cancels, but what you have to recall is that the Tn are just a reordering of the xn's. And so there's some way you can permute these around. It doesn't matter because it's just multiplication, so you can cancel these out. And maybe that 1 on top cancels with 3 on the bottom, 2 on the bottom cancels with 5 on the top, but they'll cancel out. And basically all you're going to be left with is 1 over n factorial. And so since this is free of theta, t is sufficient. And so this example is kind of has broad implications, because this statistic, which isn't a great statistic, I mean, it's frankly kind of a crap statistic, right? All you're doing is reordering your data. But order statistics are always going to be sufficient for whatever parameter. you could actually show that the data itself is always sufficient for any parameter. It's not a great statistic because it doesn't summarize anything. If someone asked me to go, okay, go summarize the data for you, and I came back and said, here's the data back, kind of in some technical sense, it's a summary. Or if I reordered it and said, I ordered them for you, kind of technically it's a summary, but not a great summary. It doesn't reduce the dimension of the data at all. But it doesn't lose any information. So it is sufficient. All the information that's in the data about theta is in the order statistics, because it's just a reordering of the data. And you could do a very similar proof to show that if I just give you the data back itself, the data is sufficient for the data itself is sufficient for any parameter, because it's just the data. Yes, all the information that's included in the data about the parameter is included in the data. It's not that interesting of a case, but it's kind of if anyone asks you to define the sufficient statistic, just give them back the data itself, right? That's the data. That's always a sufficient statistic. Okay, let's do one that is maybe a little more interesting and a little more practical. And we can go back to our normal examples from last lecture. So, example, let us have data that comes from a normal distribution. But instead of having a sigma squared, let's just say that the variance is 1. It doesn't really matter. It just makes our lives easier. Basically, we're saying sigma squared is known. And let our statistic t be x bar. We know from last lecture that x bar is going to have a normal, mu, and in this case, 1 over n distribution. And the question, obviously, is x bar sufficient for the mean? Our gut instinct tells us that x bar should be, right? Mu, for a normal distribution, is the location, and the arithmetic mean, x bar, is kind of the prototypical way of estimating location. But it seems like x bar should contain all the information about the mean. And indeed it does. And we can show that x bar is sufficient for mu. It contains all the information. So let's do it. What we need to do is check that the conditional distribution of x given t is free of theta. That is, if I condition on t, there's nothing left about theta in the remainder of the data. Okay. So as always, we can basically, I'm going to say dot, 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 right? And dot, dot, dot is basically saying that we only need to consider when x bar is t. That is, and this is this whole thing about this indicator function above. We don't need to consider cases where, so technically t could be different than the x bar that's calculated from little x. But that's a dumb scenario to consider. We only need to consider the situations where the x, where if I average these x's, they give me t. Because if that ain't true, the probability of that occurring is 0. Right? Given that the mean of them is t, what's the probability I get some x where the mean isn't t? 0. Okay. So we can skip our steps, and basically we run into this. We've run into the same situation we've had before, where we basically end up looking at this ratio. And I guess in this case, yeah, t. We'll leave it at t. It's x bar, right? So we look at the ratio of f of x, as the joint distribution of the data, over the marginal distribution of the statistic. Don't worry, we're going to summarize this all, and we won't have to do these tedious calculations for homework, but it's good to see them a couple times. Then you'll appreciate the theorem that makes this a lot easier. Okay, so what's the joint distribution of the data? Well, it's the product of the marginals. And what are our marginals? They're normal mu1. So it's 2, what are those? 2 pi, sigma squared is 1 in this case. exp of negative 1 over 2, sigma squared is 1. And this is xn minus mu quantity squared. So that I claim as the top. And the bottom, again, so t is x bar, has a normal mu 1 over n. So now we need to be a little more careful. It's, in the bottom, it's root 2 over n, because our variance is 1 over n. Exponential, negative 1/2 x bar minus mu squared. And I'm missing something, right? This should be 1 over 2n. No, it should be n at the top, right? Yeah, n at the top, right? It's 1 over 2 sigma squared is 1 over n. Okay, I think that's correct. And let's do some simplification. So the top we could simplify as, I guess this should be a 1 over 2n pi. Yeah, okay. So the top we can say is 2 pi to the negative n, because there are n of them. The bottom is, of course, 2 pi over n to the negative 1. Why not? And the top, we can push this product through. Let's push this product through. It will change, right? So the fact that I've used over and over is that e to the a, the product of e to the an is e to the sum of the an's, right? And so we're going to use this again. And we get sum, goes 1 to n of xn minus mu quantity squared. Oops, that's the top. Oh no. Let's grab this and move it up top. And the bottom is pretty much unchanged, right? I guess let's see, a negative there. Bottom is basically unchanged. Negative n over 2 x bar minus mu squared. Okay. We gotta show that we can cancel things here, right? So I'm gonna excise out this chunk and we're gonna do some algebra here. So here's the algebra. I'm gonna do this kind of fast because it's a little bit of boring algebra. We want to simplify this. Let's first square things out. This is should be not xi, but xn squared minus 2 mu xn plus mu squared. I'm going to push my sum through. This is sum of xn squared minus 2 mu sum of the xn's plus capital N mu squared. And if we might be able to do this, let's see, what if we expand this out? Let's live dangerously and see what happens here. So if we look at x bar minus mu quantity squared, this is x bar squared minus 2 mu x bar plus mu squared. Okay. So this is just some algebra. Show that things work. Let's rewrite things. For the 100th time, let's rewrite things. Negative n. You know what? Those constants don't depend on theta. They're not changing anything. Proportional, just ignore them, right? Basically what we have here is exp of negative 1/2, and then we have sum of the xn squared minus 2 mu. I'm going to replace the sum of the xn's as nx bar. I'm allowed to do that because the sum of the xn's is nx bar, right? I'm just moving, if x bar is 1 over n, the sum of the xn's, sum of the xn's is nx bar. It's a good thing to remember for this course. And then I get n mu squared. And now in my basement here in green, exponential, I have a negative 1/2, and I'm going to push this n through here, so I can push an n into each of those places. I will get n x bar squared. I will get minus 2 mu n x bar, and I will get plus n mu squared. Now that looks nice, because what happens is n mu squared cancels with n mu squared. This cancels with this, and there ain't no more mu's left. So this quantity doesn't depend on mu. So let's go back up to whatever the whole point of this thing was, right? We're looking at a conditional distribution. If I take x, I condition on t. What do I get? I go through some calculations. I do a little bit of algebra, and I can show that the ultimate thing doesn't depend on mu. This says that t, which in our case was x bar, is sufficient for mu. And that's reassuring, because we use x bar to calculate the mean, in particular for normal data. And it's good that it contains all the information about mu that is possibly there. So these examples are pretty tedious, and you start to see that they become pretty formulaic, right? I basically look at the distribution of x of the joint data over the distribution of t, and I try to cancel things out. Turns out some smart guys, and let's see if I can remember who this. Well, it's called the Factorization Theorem. Test my statistic knowledge of who actually made this theorem. I think it's who did this? Fisher and Pearson. Neyman and Fisher? Fisher and someone. Came up with a great theorem. Doesn't matter. Here's the theorem. I don't want to have to do those tedious calculations. So we're going to tell you when t is sufficient for things. T is sufficient for theta if and only if, let me write this on a new line, if and only if there is a function g of theta t and h of x, so that the joint distribution of my data can be factored, as the name of the theorem implies, as g of theta t times h of x. So what this theorem is going to allow us to do is that we don't have to do this whole conditional calculation. Basically, I did that to torture you and to make you appreciate that this is a really useful theorem. And the theorem says that I can basically inspect the joint distribution, and if I can factor things, if I can separate my joint distribution into something that depends on x but not theta, and something that depends on theta and x only through my statistic t. So maybe I should make this a capital T. It doesn't really matter. Let's just make this a capital T to be less confusing. So one h that only depends on the data, not on our parameter. And the other part of the distribution depends on the parameter, and it only depends on x through the function t, which is, t of x or whatever, right? So if I can do that, if and only if I can do that, t is sufficient for theta. Yeah, let's look at an example. It's the easiest example to look at. Well, we could revisit one of the ones we've done. So let's see. This normal one was a huge pain. Let's see if we can do that. It's always a bit dangerous when I don't prep examples. I think we can do this one. I do have a degree or two in stats. So here's our setup. xn's are IID, normal mu1, and I want to show that x bar is sufficient for mu. Tedious calculation before. My factorization theorem says that what I'm going to do is I'm going to look at my joint distribution. So let's just write out my joint distribution. And it was what? 1 over 2 pi, exponential, negative 1/2, xn minus mu quantity squared. Okay. What I want to do is I want to identify a g and identify an h and identify a t. I've given you the t in this case. In some problems I will not tell you t and I'll tell you to find the sufficient statistic. We'll do an example. Yeah, so what I want to do is I want to find the g and the h and factor it. Okay, so let's simplify this a little bit more. 2 pi to the negative n over 2. We can write like that. Whatever. Did I mess it up earlier? I probably messed it up earlier, didn't I? Yeah, surely these have 1/2. Good catch. Great. That doesn't matter. It doesn't depend on theta. It really is unimportant. What I'm left with here, as we simplified before, is the sum like this. And I'm just going to say proportional. I don't really care about things that this constant out front. And we had expanded this out before. We said it was the sum of the xn squared plus, minus 2 mu, I think we said nx bar, plus mu squared, or n mu squared. I think I'm remembering that, right? Let's go up and just look. Sum of the xn squared minus 2nx bar plus, yeah. Okay, so I got that right. And now let's break this apart. So I suppose I should really include this constant if I'm showing this as a first example. Doesn't really matter. It doesn't depend on mu. Okay, so let's see. Let's break this apart. What I want, right, so I want to pull off everything that doesn't depend on theta and depends on x, but not x bar into h, and then everything depends on theta and x bar into t, into g. So 2 pi, negative n over 2. I can break up this obviously into a product of exponentials, and I want everything that, basically want this part that depends on the x's, doesn't depend on x bar, and doesn't depend on mu. So, okay. And then what else am I left with? I'm left with this thing. Negative 1/2. We'll just leave it like this. It's a bit ugly, but it doesn't matter. This doesn't have to be pretty, it just has to be there. Okay. This, I can call h of x. Doesn't depend on mu, depends on some stuff, doesn't depend on t. It doesn't even matter if it depends on t. It depends on the x's, and doesn't depend on the parameter. And then here, I'm going to call this g of t, what did I say, theta and t. In this case, theta is mu and t. So g of mu t is and at x bar, I put little t plus n mu squared, right? So if I do this, I can replace t with x bar if it makes you happier. I have fully factored my joint into something that depends on my data, not my parameter, and then something depends on my parameter, so there's a mu's in here. But the only way that my x's come in is through x bar. They don't slip in anywhere else. There are no single x's. There's nothing but x through the x's through x bar. And so I've done the factorization. So since I can factor in this way, x bar is sufficient for theta. And that seems like a less painful calculation to do than to have to, first of all, I didn't even need to know what the distribution of t is. What if I don't know what the distribution of my statistic is? It's complicated. Don't need to. I just need to do this factorization. And I can tell you that it's sufficient. So it's a dead useful theorem for finding sufficiency. Let's do an example that we haven't seen before. We're going to do some more examples probably for the rest of this lecture on applying this theorem, and you'll have homework problems on it. So let's have our data be uniform between 0 and theta. All right, so here's my marginal. It's 1 over theta between 0 and theta, and 0 outside of that. And I want to find, can I find the sufficient stat for theta? I'm not going to tell you what it is. Of course, there are multiple. If I take any one-to-one function of a sufficient statistic is sufficient, right? So basically any function of a sufficient statistic is going to, as long as it's invertible, is going to be sufficient. I can multiply by a number. If x bar is sufficient, 5x bar is sufficient. I don't lose data by one-to-one transformations. So this is kind of a different, though. I'm not going to tell you what it is. So what you're going to do is basically, what we're going to do is we're going to apply the factorization theorem and see if we can figure out what we need to make t in order to make the theorem hold, and that will tell us what the sufficient statistic is. So the factorization theorem says we're going to look at the joint distribution of the data. What's our joint distribution? 1 over theta indicator that our x sub n's are between 0 and theta. And so this is, let's write it as theta to the negative n times this product that theta is between 0, or the x sub n's are between 0 and theta. Now, facts about indicator function. Indicator of statement A times indicator of statement B is basically, or is exactly, the indicator of A and B. Right? This thing is only 1 if A and B are both true. If either is false, the thing is 0. So the product of indicators is the logical and. So what this means practically is I have a huge product of indicators here. And so one could think of this as all of these conditions have to be true. All have to be true, otherwise the whole thing is 0. Right? If any of them is false, one of the values in the product is 0, the whole product is 0. And so what are these conditions saying? They're saying that the xn's all have to be between 0 and theta. So all xn's between 0 and theta. So what does this mean? Is there another way you can write it? One way you could write this is that the minimum has to be bigger than 0, and the maximum has to be less than theta. If that's true, that is an equivalent statement. That all the x ends between 0 and theta, and min is positive, max is less than theta. That's the same thing, right? If the min is bigger than 0, they're all bigger than 0. And the max is less than theta, they're all less than theta. So that means they're all between 0 and theta. So I could rewrite this as, using some kind of logic here, as theta negative n, indicator that what? That the minimum, x1, is bigger than 0. And now we're going to do and, so I can do a product, and the maximum is less than theta. That is a super clever trick. I know that trick because somebody showed me that trick. So if you look at that and say, I wouldn't have gotten that, neither would I. I've seen the trick. It's a really slick trick, but it's useful to know. And we'll use this a million times throughout the course, so it's good to learn it. Don't gloss over it. Figure out what's going on here. Okay. I want to find a sufficient statistic. So what I need to do is I need to convince myself that there's some g of theta and t. I don't know what the t is. We'll have to figure out that. And then there's some h of x, so that I can write this joint distribution as this factored form. So what is the way to do that? Well, I could make h of x can't depend on theta. So I'm going to pull out parts that depend on x and not on theta. This indicator function depends on the x's for the minimum. Doesn't depend on the theta. And I could make g of theta t. It has to include everything. Anything that involves theta has to be in this. So it certainly has to have theta negative n. And it's going to have this thing. So what should my t be? Well, if I make my t this, so that g of theta t is theta negative n, indicator that t is less than theta, where t is the maximum. Hey, that's a statistic. The maximum is a statistic. Then we're good, right? We've actually done it. Which means what? Which means, so t, which is the maximum, is sufficient for theta. And that's how you can use this factorization theorem to actually discover sufficient statistics. I mean, you basically have to stare at it long enough until you can see how to do this factorization. How do I choose g and h and t so that this factorization is possible? So we came up with that for this model that the maximum is sufficient for theta. Let's look at our model again, right? Our model is that the data is uniform between 0 and theta. Theta is like the maximum value that the data could take on. So not surprisingly, a statistic that captures all the information that is possible in our data is the maximum of all of our points that we collect. Is the maximum of our data turns out it's going to be a good estimator for the maximum of this distribution. So it's satisfying, actually. It makes sense. Theta is our maximum, and apparently a statistic that sufficiently captures all the information about that maximum is the maximum of our data, which makes sense. If it gave you a bunch of data and said it's uniform between 0 and some unknown number, what do you guess the unknown number is? Well, certainly not going to be less than any of the points you have. So you could, it's probably the point I have, or the maximum of the points I have. Yeah, it seems totally reasonable to me. Okay. So let's look at one more example, and then we'll prove a nice little theorem about these sufficient statistics related to what we talked about last time, which was exponential families. We'll see if we can get to that theorem today. I think we can. Let's do some more examples, because that's practically, you're going to have to do these problems on assignments, so this is practically a useful thing to talk about. Okay. And if you want to try pausing it now and trying this yourself, that might be a good idea. We're going to take data that's from Poisson distribution. So here, Poisson has a parameter lambda. Lambda is positive, right? So if we recall, the marginal distribution of a Poisson, the Poisson PDF is lambda to the x e to the negative lambda over x factorial, right? And so we want to discover a sufficient statistic for lambda. So I'll speed up a little bit here. Joint distribution, product of the xn's, of the f's, of the marginals, which is the product of lambda to the xn e to the negative lambda over xn factorial. So there's going to be a product of 1 over these factorials. That is what it is. We can have a lambda to the sum of the x of n's. I think I've shown that trick before. And e to the negative n lambda. If that was too fast, pause it and think about why these are all true. They are. So, okay. I want to factor this. I want to factor this as, right? I want to find the sufficient statistic for lambda. I need an h of x, I need a g of theta, and I need the t there for my statistic. H is pretty easy, generally, to pull out. Not always, but h is going to always be anything that you can pull off that doesn't involve the parameter. So in this case, this horrible expression of the product of the 1 over the xn factorials will pull off. And it looks like if I did my g function as lambda to the t e to the negative n lambda, so that involves certainly lambda. I guess, why do I have theta in there? It should be lambda, right? Certainly involves lambda, and if I make t, in this case, the sum of my x of n's, then that would be sufficient. So I could certainly choose the sum of the xn's. Another thing I could do, which is maybe more satisfying, is I could rewrite. So let me do a little trick here. I could multiply by n and then divide by n, right? Which would allow me to make my t actually x bar. It doesn't matter, again. Any one-to-one function of sufficient statistic is sufficient for exactly this reason. I can add in, say, multiplication. I could put a one-to-one function and then do the inverse of it, and it's all okay. In any case, either the sum or I have to like x bar is sufficient for lambda in this Poisson model. And that was pretty straightforward, I think. Notice here again, does this seem reasonable? Notice, what's the expected value of x bar in this case? Well, back up. What's the expected value of any of my random variables here, any of my samples? They're Poisson. The mean of a Poisson is just the parameter lambda. And so the mean of x bar is what? Is also going to be lambda, right? And we've probably seen this before, right? So the expected value of x bar is the expected value of 1 over n sum my xn's. I can pull that 1 over n out. I can push my expectation through the sum. And so this is 1 over n, and then I have a bunch of lambdas. I have n of them, and so I just get lambda. So indeed, it makes sense. Lambda seems like a reasonable, that makes sense. It's sufficient. Lambda's like the mean of these things. So if I want to estimate the mean, I have a bunch of data I've collected from Poisson. It has some mean lambda. I don't know what the mean is. What should I estimate the mean as? X bar. Yeah, I could buy that. That makes sense to me. So I think that basically the last thing we want to do here is talk about a theorem relating exponential families and sufficiency. Okay. So the theorem goes as follows. And so now you're going to get a little bit of a sense, start of a sense about why exponential families are useful. If we have some random sample from some parameterized family of distributions, f theta, that is an exponential family. And so let's say f theta is an exponential family. Then, right, so we'll just write this out, right? An exponential family says I can write this as h of x, c of theta, exponential of t of x times w of theta, right? Suspiciously starts to feel a lot like a factorization. And indeed, not surprisingly, you might be able to see it. The theorem says if we have this from an exponential family, then t is sufficient for theta. So that's the theorem. And really not too hard to prove. Kind of just have to point at the form of the exponential family, right? All I have to do is tell you G, basically, H is already H according to the previous factorization theorem, the same H's, right? So if I let G of theta t be equal to C of theta exp of, let's see, t times w of theta, and then my joint distribution is h of x, g of theta t. So t is sufficient for theta, which is super cool. So if you have an exponential family, and you had to write it out, you already know a sufficient statistic. So maybe we should just write one example. When we were doing the exponential families, we saw that if I have data that comes from an actual exponential distribution, different than family, distribution, right, of the form, whatever, that is fx is lambda e to the negative lambda x. This is my marginal distribution. Then we saw that, how could we write this out? So this is my joint distribution, which is the product something like this. And ooh, how much do I want to do out here? Let's see. Something like that. We had talked about how that was t in the exponential family. That is also going to be t as a sufficient statistic, and it's almost yeah, I mean, it almost goes without saying. You can see how it's both exponential family t and the sufficient statistic t. So that's really nice. And it gives us a whole bunch of common distributions that we know pretty easily how to find a sufficient statistic for them. So I think this is a good stopping point. We're pretty much at time here. We can do a real quick review of the lecture, and the lecture is about sufficiency. So it's kind of the first major property that we learn of an estimator. And the statistic is called sufficient. It has this kind of complicated definition, technical definition, which is that, if I take the data and I condition on the statistic, then the resulting conditional distribution doesn't depend on the underlying parameter. What that is trying to capture is that if I know the statistic and I condition on it, the remainder of the data doesn't tell me anything about the theta, about the unknown parameter theta. And so all of the information is about my unknown parameters contained in the statistic. And so we did some examples kind of, and you might go back and do them now with the factorization theorem. We did some really tedious examples to start using that definition. And we saw, for example, that you can show, for example, that either the whole data or order statistics are always sufficient, okay? And we looked at like the mean for normal data, but we have this super useful factorization theorem that says if I can factor my joint distribution in a certain way, then I can find a sufficient statistic where I can show that things are sufficient. And so we looked at some examples of that. And for exponential families, we can pretty easily pick off the sufficient statistic in this way. So we'll stop there, and we'll pick up here next lecture.